Okay, everyone, good morning. Welcome back to our lectures on MSD 780. Today we're going to jump into the last studies theme, which deals with optimization and dynamics. We're going to look at the integration of the dynamic queue optimization workbench into the DAP-BC workbench. Before we get to that, just a quick admin point that I also want to make. I see I received a few emails from students asking for a possible extension of assignment 1. So if I quickly look at our schedule, I think what we can do, so currently the deadline is on the 7th of October. What we can maybe do is rather extend it to the 11th of October. So I'll extend the deadline for assignment 1 to the 11th of October. I'd rather do this with assignment 1. For assignment 2, we're not going to be able to do that, mainly because that assignment is going to be due fairly close to the exam period. So that will probably be due on the 8th of November. I'd also like to rather give students enough time to get assignment 1 in order, since assignment 2 can possibly follow on assignment 1. You'll probably be tasked with setting up a mechanism and then doing some sort of a parametric study on that one. So if you want to, you're going to be able to carry over assignment 1's mechanism to assignment 2 and then just perform some optimizations on that. So the second assignment I'll make available, I think, a bit later this week, but it will be due on the 8th of November. And then the first assignment will then be moved to the 11th of October, that deadline. Okay, so with that being said, we can now jump into our last study theme, optimization and dynamics. So what we're going to try and do over here is to integrate the dynamic queue workbench. You'll see over here we talk about the dynamic queue optimizer into the DAP-BC workbench. And this is going to allow us to do some parametric studies on some of the examples that we did and some additional mechanisms that we want to look at. Up to now, we've considered fairly stock standard application examples. We know what the dynamic properties are. We know the geometry of the system, the stiffness of any springs and damping coefficients of any dampers that we had in the system. We can now go one step further and ask, well, what would happen with the system and a possible objective function if we now go and vary some of these parameters? If I use different spring stiffnesses, if I move the distance between two actuator legs, how will that influence, for example, the actuator forces? And what we aim to do over there is then to sort of minimize one of these objective functions. So we can, for example, minimize the actuator forces subject to these design parameters. So subject to the distance between the actuators, as an example. Now, before we jump into dynamic queue optimization, just a quick review perhaps of the DAP-BC workbench and everything we've discussed up to now. So the DAP-BC workbench we now know is a body coordinate formulation. That's what the BC in DAP-BC stands for. And in comparison to the joint coordinate and the point coordinate formulations, the body coordinate formulation is a bit more elaborate than its counterparts. So the number of equations generated by the body coordinate approach is significantly more than those generated by other formulations. And this makes it quite useful in a computational or a numerical environment. We wouldn't want to use the body coordinate formulation to perform pen and paper calculations. We'd rather want to generate these system of equations within a numerical environment such as MATLAB or Octave and then solve it like that. And one of the reasons for this is that we don't need free body diagrams. So the analysis is governed purely by numerical methods. And we saw from our analysis of the Jacobian matrices as well, if we know what the type of kinematic joint is, for example, we can easily set up those Jacobian matrices without even considering a free body diagram. And that analogy can be extended through to other calculations that we also do. In addition to that, we also know that the BC formulation is a general purpose approach, so it can be applied to any choice of multi-body system with any number of bodies. And we saw this when we looked at the application examples. We could easily go from one application example to another without having to re-derive any of the formulas. They are pretty stock standard across all of the examples. So of course, the general purpose approach is very useful when you have versatility across mechanisms. So you have a bunch of different mechanisms that you want to analyze. So then a general purpose approach would definitely save you time on that front. However, some of the disadvantages of these general purpose approaches is that they tend to take longer than special purpose programs. So a program that you develop for a specific mechanism, for example, a slider crank mechanism. The drawback, of course, of a special purpose program is that if you want to now go from one mechanism to another, you have to go and rederive all of those calculations. But for the purposes of MSD 780, since we're working with a whole array of different mechanisms, a general purpose approach is quite applicable to our problems. Okay, and then finally, we also know that it's a numerical approach. The BC formulation is numerical in nature. So we have direct access to the function scripts and the numeric procedures. We're not limited by some user interface, and this provides us room for expansion. And this is now where the optimization counterpart is going to come in. We are essentially going to attach or expand the properties of the DAP BC workbench so that we can now go and perform optimizations. Okay, so then moving over to section 2, we're going to specifically focus on dynamic queue optimization. Now, dynamic queue is essentially an extension of the previously proposed leapfrog optimizer with constraints, or ALFOP-C algorithm, that was developed by Professor Jan Snyman back in 2000. So the idea behind the dynamic queue optimization is to provide simplified Hessian matrices, gradient matrices, all those definitions, so that you have to define less when you perform these optimizations. But it still carries over the gradient-based characteristics and advantages of the ALFOP-C algorithm. So to perhaps give you a few advantages of the gradient-based optimization, and this is what a dynamic queue optimizer is. These type of optimization algorithms deal with function derivatives to obtain minima in the data, and minimal inputs are required. So it's typically a good idea to compare this with something like a global optimization technique. For those of you who are familiar with that, something like a genetic algorithm, a particle swarm optimization, those kind of things you usually need to give quite a lot of population parameters when you perform these calculations. So you need a large array of inputs to calculate the properties or the minimization of the objective function. In the case of a gradient-based approach, we minimize the number of inputs that we need to give. So we'll perhaps only have to give the objective function, any constraints that we have, and then the gradient vectors as well. And that should be sufficient to solve the problem. Another advantage of gradient-based optimizers is that they are extremely efficient for complex engineering problems where multiple function evaluations are required. And an example of this would be when we looked at our application examples, we saw over there that the function evaluations, we're not working with a small number of function evaluations, especially if you're considering perhaps a friction model and you have that stiction friction over there, that significantly increases the number of function evaluations, which means that the amount of time that you require to solve the problem is also going to increase. So the efficiency of the optimization can then be improved by using a gradient-based optimizer. And then although you have a lot of function evaluations, it is expected to converge fairly quickly. It also provides a simpler approach to dealing with boundary conditions. So since boundary conditions are simply linearized inequality constraints, we can separate them from our standard inequality constraints, and we can analyze them in a linear fashion as well. So we're going to look at that in the general definition in just a moment. And then another advantage is that it's more applicable to problems with many design variables. And this is typically the type of problems that we also work with in dynamics or mechanical engineering in general. We have quite a lot of design variables that we want to investigate and see how they are going to influence the objective function. Now, of course, gradient-based optimizers also have some disadvantages. In general, they are less feasible for problems where noisy data is present. So you can imagine that if you have a gradient-based approach, you depend not only on the objective function itself, you depend on the gradient as well. And in that case, if you have a lot of noisy data, it's going to influence the localized gradient calculations over there. So in that case, you're going to have to perform some sort of a filtering process to perhaps get a smooth curvature on your objective function. Now, in general, for the DAP-BC workbench and the dynamic analyses that we perform, you should get fairly smooth curvatures out over there. Although you're using iterative techniques, the overall objective function that we're going to look at is probably going to be smooth in nature. Okay, then we also need to consider the initial variables or the initial the starting points that we use for our design. And these have a significant impact on the convergence behavior. And this ties in with this third point that we have over here, that it's more likely to converge on a local minimum than a global minimum. Okay, so if you are interested in a global minimum, what you can perhaps do is use something like a gradient-based approach, and then just use different starting points and see to which point each of these initial designs converge. Of course, the smallest among these will then give you the global minimum. The alternative, of course, is then to use a global optimizer. Overall, these tend to take significantly longer to solve. So my suggestion would also rather be to use some sort of a gradient-based approach and use different starting configurations and see how that influences your global or your minimized objective function. Right, so with that being said, we can then go over to the general definition for the dynamic Q optimizer. And this was also proposed by Snyman and Hay in 2001. What this essentially tells us over here is we want to minimize some objective function over here, f tilde x. And this f tilde x, the objective function, is influenced by a set of design variables over here. So x is then a vector which goes from x1, x2 up to xn, where n is the number of variables that you have. So if I change any of these variables, the objective function is also going to change. And then we say it's subject to a set of inequality constraints. And you'll notice the form of this inequality constraint is always smaller than or equal to 0. If we have something greater than or equal to 0, we just have to rearrange the terms, so take them to the right-hand side so that we once again end up with smaller than or equal to 0. Then we also have equality constraints. So this is simply any constraints that have to equal 0. And then these two lines over here refer to the lower and the upper bounds that we place on our design variables. And you'll see in this case, once again, we handle this separately from our inequality constraints, since these are linearized versions of these constraints. So we can easily evaluate them instead of going into all of the difference methods associated with the inequality constraints. And then the last line over here is simply a tolerance that we place on what we call a move limit. So this simply says that when the optimization is being performed, the step size between two consecutive design variable selections needs to be smaller than or equal to this delta squared. We're going to look at this as well in the guide document that has been made available. Okay, so in general, or in summary, the dynamic queue is a reasonable first-order approach to optimization, and it's definitely more than sufficient for the calculations that we're going to perform in DAP-BC. Since we expect to work with smooth curvatures, we don't have to worry about any global optimization techniques. We can simply rely on a gradient-based optimizer to solve these problems. All right, so then moving over to section 3, we're first going to focus on optimization-only examples. So before we jump into DAP-BC, I first just want to look at dynamic Q. Since dynamic Q is a standalone package, we can use dynamic Q to just solve a few relatively trivial problems or analytical equations and see how we handle inequality constraints, equality constraints, any side constraints, and what the effect of any other input arguments are on the system. So before we jump into that, you'll see if I expand over here, you'll have this general procedure and guide to dynamic Q. So this was written by Alex Hay in 2002 as an addendum to the dynamic Q program that he set up. So if I click on this file over here, it should open up the guide document. Okay, so we're just quickly going to read through this. So the dynamic queue optimizer has a bunch of different files or input scripts that we're going to make use of. Now to access this, you'll see on the on ClickUp, you'll have access to a DAP-BC dynamic queue hybrid workbench. So it's a zip file that you can download. If you extract it, then you should find this DAP-BC dynamic queue hybrid workbench rev01 file over here. So if you open this folder, you'll see it looks more or less the same as what we had for the DAP-BC12 workbench. In this case, we just added this dynamic queue over here, and this is the optimization part that we attach to the DAP-BC part. So for now, we're just going to focus on dynamic queue, so you can double click on this subfolder as well. And then you'll see all of the scripts that are used to perform the optimization. Now, the ones that we're going to focus on is the fch.m and the grad fch.m files. So I'm just going to double click on them, make that a bit bigger. Okay, so then we can go back to the guide document and just see what we need to give as input for these files. So the steps over here says, firstly, we need to determine the objective function that needs to be minimized. The inequality constraint function C, which needs to be smaller than or equal to 0, and then the equality constraint functions H, which must be equal to 0. And we need to edit all of them into the function file fch.m. Now, if I look back at the fch.m file, which is this one over here, you'll see that I need to give it 3 inputs, and this corresponds to what we said in the guide document. We have F, C, and H that we specify. And there are a few examples over here. I think if we look at this example, you'll see F doesn't have an index over here because we're only working with a single objective function. Then C can be given as C1, C2, C3, depending on the number of inequality constraints that you have. And then the same with H as well. So H1, H2, H3 if I have multiple equality constraints. All right, so if I've defined that, then I can go over to the grad fch.m file. And in this case, I just need to give the gradient vectors of the objective function, the inequality constraints GC, and the equality constraints GH. So this can either be given as an analytical function, so that is what we did over here. In this case, since I do have the analytical equation available, it's easy to find these gradient vectors by simply deriving the objective function, the inequality and equality constraints. However, if you're working with a discretely defined function, then you'd probably rather rely on this finite difference method over here. So using the forward or the backward or the central difference method to go and calculate your gradients. And this over here, I should perhaps just do this first. Okay, so this part that we have over here, the FD flag equal to 1 up to this end, this is more or less a standard definition for the, I think this is the forward difference method since we're using plus delta x over here. So if you're unsure about these analytical gradients, you're just going to use the forward difference method over here. And this is pretty stock standard. You can just go and change the delta x. Usually we'll just use 10 to the power of minus 8. This value is usually determined by a sensitivity analysis, but we're not going to delve into sensitivity analyses for DAP-BC. So if you have to change this value, we will give it to you. Otherwise, you can just use the 10 to the power of minus 8 standard value over here. Okay, so I'm just going to suppress this for now. Okay, and then if we head back, so now once we've defined the gradient vectors for the objective function, inequality constraints and equality constraints, then we can actually go and just run the actual problem. So if your problem has, okay, before we actually get to that, just an important step over here as well. If your problem has no equality constraints, then H should be equal to 0 and H should be equal to an empty list, and GH should also be an empty list. And then if you have if your problem has no inequality constraints, then C needs to be equal to an empty list and GC needs to be equal to an empty list. So I think there's just an error over here with how it was written. In this case, the second point should be if the problem has no equality constraints, and then the first point should be if the problem has no inequality constraints. Since C refers to inequality, H refers to equality. Okay, so now they say to solve your problem, you can go to the MATLAB command environment and type in the keyword dinq, and then over here you'll have some vector that you have to give as input as well. And this will simply solve the problem using dinq and starting values x0. So this, we also always have to give the starting point as an input, or the starting vector as an input. And this is what this 1551 is over here. Now, in addition, if you have side constraints, then they are handled separately from the inequality constraints, and they are specified using input arguments low and up, corresponding respectively to the lower and upper limits of the variables. So these input matrices are then defined as low, which is a number of lower inequality constraints or lower bounds by 2 matrix, and then the upper is the number of upper side constraints that we have by 2 matrix as well. So to better understand how we define this, if we look at an example where we have x1, which must be smaller than or equal to 15, this is what this essentially says over here. So you can replace this equal sign with a smaller than or equal. Then you have x2, which needs to be between 1 and 10, x3, which needs to be smaller than or equal to 20, and then x4, which needs to be greater than or equal to 3. Okay, so if I then set up the low and up vectors over here, low is then equal to, in the first column over here, we have 2, 4, and these are the 2 variables that have lower bounds defined on them. So if I look at x2, I can see that it needs to be greater than or equal to 1, so that's a lower bound. And then on 4, it needs to be greater than or equal to 3. So in the second column, I simply give the actual value for the lower bounds. Then for the upper bound, I have on x1, 2, and 3 upper bound, and their values are 15, 10, and 20. So I just populate that in the second column over here. Now, to include these constraints in the call to dynamic queue, we simply type in this x0, which is equal to 1551. The lower bounds we type in, and then we also give the upper bounds. And we just need to make sure that the form of these lower and upper bounds are also correct. So you want, in the first column, you want the design variable index. In the second column, you want the actual value for those lower or upper bounds. Okay, and then we can run it using the keywords x0, low, and up. Now, in general, the dinq function actually takes in a bunch of different arguments. If we don't specify these arguments, then default values are used for them. So if we look at this definition over here, so the xf are the output variables that I want to get, and then dinq uses all of these arguments over here that are then discussed in this section over here. So if we look at the outputs, x is going to be our optimal solution or our optimum design variables. So the design variables that we get once the optimization has converged to a minimized objective function. And that minimized objective function value is then given by f. So that is also known as the optimal function value. Considering the inputs, x0 is your starting points, as we know. Low is the lower bounds, up is the upper bounds, and now we also have this DML, which is then the move limit, and this ties in with what we discussed under section 2. So if I just expand this again, this basically pertains to this last point that we have over here, so smaller than or equal to delta squared. Okay, so the move limit should be approximately the same order of magnitude as the radius of the region of interest. And we can go and calculate this radius by using the square root in. So the square root of the number of design variables that we're working with multiplied by the maximum variable range. So if I, for example, if I'm working with, let's say, three design variables, and x1 and x2 has a range of 0 to 1, and x3 then has a range of 0 to 100. Then I know the maximum variable range is 100 minus 0, and I simply multiply that by the square root of 3. And that then gives me an indicator of the move limit. If I don't specify this, then the default value of 1 is used. Okay, then we also have an X tolerance. So this is the convergence tolerance on the step size, and this is also optional. The default value over here is 10 to the power of minus 5. The F tol is then the convergence tolerance on the function value. So this is also given as a default value of 10 to the power of minus 8. Now, to better understand X tol and F tol, X tol is essentially when you perform an iteration optimization, the norm or the difference between two consecutive step size values or step size vectors needs to be smaller than or equal to 10 to the power of minus 5. And then for F tol, it just means that when it calculates the function value at each iteration, if that function value's difference between two consecutive iterations is smaller than 10 to the power of minus 8, then it can converge on this convergence characteristic over here. Then we also have C-lim, and this is simply a tolerance that is used for determining whether constraints are violated. So this is also optional. If it's not defined, we simply use the F tol and we multiply that by 100. So if I have an F tol of 10 to the power of minus 8, then C-lim will be 10 to the power of minus 6. So if my inequality and equality constraints are smaller than 10 to the power of minus 6, then I've converged based on the constraint convergence tolerances over there. Then I also have NP and NQ, and these are the number of inequality and equality constraints that I have in the system. So they are both optional in the sense that both NP and NQ can be determined automatically if they are not specified, but at the cost of an extra function evaluation. So in general, this function evaluation doesn't take too much time, so we can simply neglect these two values and the system will calculate the number of constraints in any case. And then lastly, we have K loop. So this is the maximum number of iterations. And what this says is that if I don't reach X tol, F tol, or C-lim, then I need to continue iterating until I reach, in this case, a default of 100 iterations. I can also make this 10 or 20 iterations depending on how difficult the problem is to solve. So in this case, if it terminates on the number of iterations, usually you won't get good convergence behavior. So ideally, you rather want to converge on the X tol or the F tol. If any of these values are then default, you can use the square brackets or the empty list over here to activate the default inputs. And this is done between two input arguments that I want to give. So for example, if I know what my starting point is, so starting point is not an optional value, I always have to give that as an input. But I know what the starting point is and I know what the move limit has to be. Then I need to place these two input argument placeholders before I can specify the move limit over here. Okay, so this will solve the problem using DINQ and a DML or a move limit equal to 5 and return the optimal solution X and corresponding optimal function value F. And then lastly, just to plot the optimization histories, and this is quite important if you want to visualize the convergence behavior, especially on the objective function and the variables. Then you can do this using the history.out file. So this is already programmed into the dynamic queue solver or the DINQ solver. So the history.out file contains the complete optimization histories of all variables, the objective function, and all constraints. These can be plotted by running the script file histplot.m. By default, this script is called at the end of DINQ, but this can be disabled by setting this prn constant equal to 0 at the beginning of the DINQ file. And this is in line 107. So if I just go back to the Octave environment over here and I go to DINQ, then you'll see in line 107, which is this one over here. At the moment, it's set equal to 1, so it is going to plot the optimization histories. If you don't want to plot it, you can just set it equal to 0. All right, so that then wraps up the, so this wraps up the guide for now. Are there any questions so far on this thing? Okay, just want to check over here as well. Okay, so I think we're good for now. All right, so with that now being said, I can perhaps just provide you a quick summary as well of what is then discussed in those files. So we typically have a 6-step process that we go through when we want to perform an optimization. So firstly, we want to define the objective function under the fch.m file. Then we want to define any constraint functions also under fch.m. Then we define the gradients of the objective function and the constraints under grad fch.m. Now, if the function is analytically known, we can define the derivatives analytically. Otherwise, if the function is not known or it's discretely known, we can use a finite difference approach. And it's typically good practice to just use the forward difference method. You can also use backward. The central difference method, however, especially if you're working with dynamic problems, tends to take significantly longer since it has to perform both a forward and a backward difference method. So we instead just rely on the forward difference method in this case. Once step 3 is done, then we can go over to step 4, and this is simply defining the starting point or vector x0. And this is not an optional argument. We always have to give this as an input to the optimizer. We also define the convergence tolerances and limits. And finally, once all of these things are defined, we can go and use the dinq.m file to perform the optimization. So this is perhaps better illustrated through application or example problems. So if we first look at example problem 1, we can consider first a single variable function with more than one local minimum. And this is then shown in this graph that you have over here. And the function is also given f of x equal to x to the 4th minus 5x cubed minus 2x squared plus 10x plus 5. And we can see over here, if we plot it analytically, we see that it has 2 minima on this graph over here. So in this case, this minimum that sits over here between 0 and minus 1 is a local minimum. And then between 3 and 4, we have a global minimum. This is the smallest attainable value for the objective function. So the function is analytically known, which means the gradients can also be defined analytically. And we assume that there are no constraints or boundary conditions that are specified on this system. And now we have 2 exercise problems that we have to do. Firstly, case 1 says we need to use a starting point x0 equal to minus 1.5. And before we do this, we first have to go and define our objective functions and constraints. In our case, we don't have any constraints, so we're just going to focus on the objective function and then also its gradient vector. So if I go to the Octave workbench and I open up fch.m, I'm just going to suppress this, and then I'm going to head back to, I think it was example problem 1 over here. So if I just say, let's just delete this. All right, so since I'm working with the objective function that I want to specify, I'm going to call it f. So I'm going to say f is equal to, and now I just have to refer back to the function that I have over here. So it says x to the 4th minus 5x cubed minus 2x squared plus 10x plus 5. So in my case, since I'm only working with a single design variable, I'm in any case going to include just its index. So it's going to be x1 dot to the 4th. I think it was minus 5 times x1 cubed minus 2 times x1 squared, and then I think it was plus 10x plus 5. So then I'm just going to say plus 10 times x1 plus 5. All right, so now I've defined the objective function. I don't have to worry about any constraint definitions. In this case, since I don't have any constraints specified, you'll see in these last lines 71 to 76, it says that if C or H does not exist, then I need to set their lists as these empty lists. So this is already included as a clause if you don't specify C and H above it. Okay, so then I just have to include the gradient vector as well. And if I go up over here, it's going to suppress this again and then focus on example problem 1. Okay, so for this problem, we only have df over dx1 that we have to worry about. So that's the one that I'm going to derive. So it's simply df over dx over here. So it's 4x cubed minus 15x squared minus 4x plus 10. So if I take this over, it's just going to be, perhaps I should just copy this one over and use it as a comment, and it will be easier to define it. Okay, so what I'm going to do is just call it GF and then index it as 1. And this is then going to be equal to 4 times x1 cubed minus 15 times x1 squared. Then it is minus 4 times x1 plus 10. Okay, and then I'm just going to delete this line as well. Right, so now I have both the objective function and its gradient vector available. I don't have any side constraints that I have to worry about, so that's also fine. If I quickly look back at the instructions, so I've now completed steps 1, 2, and 3. Then I need to define the starting point or vector. Convergence tolerances, I don't have to worry about. They didn't give me any custom values over there, so I can just use the standard values. And then I want to run denq.m as well. And these last few steps I'm just going to perform within the command window itself. So if I head to the command window, then I'm first going to say x naught is equal to, and in this case I think it was minus 1.5 for the first problem. And then I just want to run dynamic q, so I'm going to say x f is equal to denq, and I just give it x naught as an input. Right, so if I now look, I'm first going to just look at the actual iterations before I jump into the histories. So if I look at iteration 0, I can see that it starts at 7.4375 for the objective function value, so the value of f of x, and this is indeed at minus 1.5. Then it runs through a bunch of iterations, and then on the 6th iteration, it considers itself converged on a value of minus 1.3526. And the x norm in this case is then 1.006, so 10 to the power of minus 5. And then the RFD value, which corresponds to that F tol convergence tolerance, is then 10 to the power of minus 9. So since this value is smaller than 10 to the power of minus 8, it terminated on the function value. Okay, and this makes sense if we look at the function value as well. We can see that for these last few, perhaps iterations 4 to 6, we can see that the value of the objective function changes with very small increments. So it's minus 1.3525, and then at the end it's 2.6. So it's very small value, so it makes sense that it converged over here based on the RFD values. And at this point, it then found that the optimal design variable x1 is then minus 0.854, sorry. And then if we just look at x and f as well, we can see that it is indeed minus 0.8535, and then f is minus 1.3526. So to just validate these values, since we do have an analytical function available, we know that we now started at minus 1.5 for our optimization. So that point is situated somewhere around here. So what the system does is determines the gradient at this point. It finds that it's decreasing in this direction, so it's going to move towards this minimum over here. Once it reaches this minimum, or a value fairly close to this minimum, if it now tries to do the gradient to this side, to the right, it's going to find that the gradient now increases, or it's positive. So it goes from a negative to a positive gradient. So the system then says that this needs to be a minimum, and it simply converges on this. So it makes sure that its step sizes go small enough so that it converges to this red X that we have over here. Okay, so depending on, well, in this case, minus 1.5 now converged to this local minimum over here. Now we can perhaps also investigate what the effect is going to be if we look at the starting point x naught equal to 2. And before I do that, I just want to go back to the objective function histories for that previous problem. So if I first open up the objective function history, then you'll see that indeed I first started off with a fairly large or a relatively large objective function, and then it started to decrease. At iteration 3 to 6, it seems that the objective function plateaued out. So this shows that it indeed converged, or it shows good convergence behavior based on the objective functions. Then I can also go and visualize the variable history. So initially I can see that there are some spikes in the variable history, or relatively large changes in the value for the variable, but after iteration 4, so iterations 4 to 6, the variable once again plateaus over here. So this also shows good convergence behavior, right? So I can consider the optimization of this problem well validated. Okay, so now I'm just going to rerun the problem for a different x naught value. So I'm just going to say clear all, close all CLC. And now I'm just going to redefine x naught, and I'm just going to make that 2.0. And now if I run xf equal to dimq x naught, it once again took 6 iterations to converge. But if I now look at the convergence behavior, I can see both the X norm and the RFD values are now smaller than their respective tolerances that I specified. So this means that the system terminated on both the function value and the step size. And this is excellent convergence behavior. If you can find this for a problem, then it shows that you have convergence on both your variables and your function values. If we look at the final value over here, we can see that that is 3.84 for x1. If I just look at the function value itself as well, I can see that it does decrease from -7 up to -51.8. So that also shows that the objective function is minimized. X and f is just printed out over here as well for convenience sake. And if I now look back at my analytical graph over here, just to validate it. So in this case, I started at 2 over here. So the optimization then finds that the gradient is decreasing to the right. So it's going to continue stepping to the right until it finds a value fairly close to this minimum that I have over here. So in other words, at this point, we know to the left I have, or in this case to the right, I now have a positive gradient. But moving from the left-hand side to this point, I had a negative gradient. So this has to be a minimum, and the system simply converges on this minimum over here. And since I now started at 2, the system converged to a global minimum. All right, so this shows that the choice of initial values has a significant impact on where the dynamic queue optimizer will converge. And this is one of the points that we listed under the sort of a disadvantage, but also something that you just have to take into account when you're doing these problems. Be wary of where you specify your starting point, since it might converge to different solutions. If we just look at the objective function history as well, we can once again see that decrease at iteration 3, or actually iteration 2, it seems to plateau out once again, so good convergence behavior over there. And then for the variable history, we can also see at around iteration 4, the values plateau out. So this also shows good convergence on the design variables. Okay, so this is a fairly simple example which only considered a single design variable. Of course, if you're performing these type of calculations, you're probably not going to have an analytical equation available. And if you're working with maybe 1 or 2 design variables, then it's going to be easier to solve this either graphically or simply using one of Octave's built-in functions. But once you start working with multi-dimensional problems, then the dynamic queue optimizer starts to become more advantageous. Okay, so any questions on example problem 1 so far? Okay, see we don't have any questions over here as well. All right. So then we can move on to example problem 2, and this extends the dimensionality of the problem a bit. And we also consider an oscillatory problem over here. So we consider a 3D plot with a known analytical equation. Now, although still possible, this equation is much more complex to solve analytically and graphically as well. It's going to be difficult to find the exact point where we have a minimum on this graph. And the function for this is f is a function of xy, which is equal to y sine x minus x cosine y. Okay, so a complex or a combined trigonometric function that we have over here that we can solve using dynamic Q. And in this case, we're going to assume that x1 is x and x2 is equal to y. So this is simply to correspond to the formulation that we have over here at the top. Okay, so then we want to run the example problem for, I just want to see if we have, yeah, so over here we have the starting point, so I'm just going to collapse that for now. So it says that we have starting points x1, x2, which is minus 3.5 and 6. So I first just want to go and set up my objective function and its gradient vectors subsequently. So I'm just going to clear all, close all CLC over here again. And if I now head back to fch.m, I'm just going to compress or comment out this example problem 1. And now I just want to focus on example problem 2. So let me just uncomment this one. Okay, so I already typed this one in. So this is simply y sine x, so x2 times sine x1 minus x cosine y, so minus x1 times cosine x2. It's important that even though I'm working with x and y in the analytical equation, I always need to assign some sort of an index when I specify my design variables. So that's why I use x1 equal to x, x2 equal to y. It's just the way that dynamic Q is set up. Right, so then I also don't have any inequality or equality constraints, so I can ignore that. And then I want to head over to grad FCH to now define the objective function's gradient vector. Okay, so this was defined over here, but to better understand this, you'll see that we say GF1 and GF2. So if I'm setting up my vector in this case, and I'm just going to try and draw it over here in Paint, but if I'm working with df over dx, where x is now a vector, so a multi-dimensional vector that I have over here, then it means that my gradient vector is going to be a column vector where I'm basically working with df over dx1 as the first derivative. And then in my case, I'm only working with two design variables. So the second entry over here will then be df over dx2. Okay, so this is then the column vector that I'm going to try and set up. So if I look back at the equation that I have, this mainly tells me that df over dx1, or the gf1, is then going to be this one with x1 being the variable. So in this case, it will be x2 times cosine x1 minus cosine x2. And that is what I typed in over here. Then gf2 is then df over dx2. So then that equation will become sine x1 and then minus x1 and then multiplied by minus sine x2. So it's going to be sine x1 plus x1 sine x2. And that is what I also typed in over here. So that seems to correspond. Okay, so now my objective function, my gradient vector is set up. Now I just have to go and specify the starting point. And in my case, it's then going to be x naught equal to, if I look back at this, so that would be minus 3.5 and then 6.0 as well. Actually, I just have to leave out the comment over, or the comma over there. So it gives me something like that. Okay, and then I'm just going to type in xf again, which is then equal to den q x naught. And if I run this one, I can see now it took substantially more iterations to solve. From a computational time perspective, it didn't take too much longer to solve the problem, but we can see the iterations are now significantly more. We now have 18 iterations that it requires. Okay, and in this case, we can see the X norm also shows relatively good convergence behavior. Over here at the last few iterations, we can see it's -3, -4, -3, -5. But it's perhaps better to look at the function value convergence, since the problem terminated on the function values. So in this case, we can see we start off with -1, -2, -3, -4, and then we have -6, and then the final value over here is 10 to the power of -10. So smaller than 10 to the power of -8 means that it terminated on the function value. If I look at the optimized design variables as well, we started off with -3.5 and 6, and then after 18 iterations, we found it to be -1.65 and 10.1. And then the final objective function value over there was -11.357. And this is also a clear decrease in the objective function if we look at the very first iteration, which was 5.5 for this value. All right, now if I look at the objective function history as well, we can once again see that convergence behavior after about, I think this is iteration 11 or so. We can see that it once again plateaus out on the objective function history, so that shows good convergence behavior. And then if I look at the variable history as well, we can see that after, I'd say maybe over here somewhere, so after 14 iterations, we have a plateau in the design variables as well, once again showing reasonable convergence behavior over there. Okay, so if we then perhaps compare the values to what we have on this graph over here, you can already see that it's relatively difficult to see where the optimized solution is going to sit, but in this case it says that it's -1.65, 10.1. So it seems to be in the X direction, -1.65, and then 10.1 will be following this through. So it's, let me just see, so it's going to sit somewhere beyond this point, which is fairly difficult to see. So trying to validate it from a 3D perspective is going to be difficult. But at least we know from the objective function histories that we do see good convergence behavior and a good decrease in the objective function over there. So that gives us confidence in the results. And this then also illustrates why the dynamic Q optimizer is important. We won't be able to always see the graphical minimum, so we instead need to rely on numerical methods to solve the minimized solution. Okay, so if you want to, you can also just go and check out the objective function histories and stuff over here. So all of the graphs that we show in this lecture have been populated under the mind map. Okay, so then we can move on to example problem 3. And this is perhaps more representative of the type of problems that we want to solve. So we can consider a multi-dimensional problem where graphical solutions are not readily available. And the example that we're going to look at is this example by Alex Hay, which was part of his 2002 code that he set up. And the function requires you to minimize the objective function that is given over here with 4 design variables. So we're not going to be able to represent this graphically. Subject to C1, so now we have a single inequality constraint, which is smaller than or equal to 0. And we also have H1, which is our equality constraint, and that is equal to 0. So we quickly looked at the objective function gradient previously, but if we have a multi-dimensional problem, so more than 2 design variables, then this is just the form that we're going to use. So we have an n by 1 column vector that we generate, where n is the number of design variables. The gradient vectors associated with the constraint matrices are a bit more difficult to analyze. In this case, you're going to have an m by n matrix that you have to construct. So if you look at how we construct it, we say if you're moving across the rows, then the constraint that you're going to analyze is going to change. So C1, C2 up to Cm. but the design variable towards which you're deriving remains the same. If we work across the columns, then it means that the inequality constraint remains the same, but the design variable towards which we derive changes. And then the same also for this dH over dx, so for the equality constraints as well. In our case, we will thus end up with a 1/4 column matrix. So in that case, we are working with only a single constraint, so only with a single row, but we have 4 different design variables, so that's why it's 1/4. And then the same also for the dH over dx, which is also going to be a 1/4 column matrix. Right, or a row matrix rather, sorry. Okay, and then we also have some boundary conditions that we want to specify. So this simply says that for all of the design variables, they have to be between 1 and 5. And I need to just allocate this as well when I'm performing the dynamic queue optimization. All right, so if I compress that again, then they also give us the starting points over here. So x1, x2, x3, x4, and that's 1, 5, 5, 1. So this corresponds to the example that we had over here in the guide, which was 1, 5, 5, 1. So this is simply the problem that they're referring to, the basic example that has been included. Okay, now I'm just going to clear the workspace over here, move back to the fch.m file. And now I'm just going to compress example problem 2. And now I'm going to look at this example Hay 2002. So I'm just going to uncomment this. And this is simply just the previous calculations or the equations that I typed over into this file over here. So we have x1 multiplied by x4, and then in brackets we have x1 plus x2 plus x3, and outside the brackets plus x3 as well. And then for C1 and H1, they also correspond to the 2 functions that I have over here. So you can go and validate that as well. But you'll notice that even though I'm working with a single variable or a single inequality constraint and a single equality constraint, I still include the indices in this case. So it's just good practice to do that to ensure that the formulation remains constant with something where you would have multiple inequality constraints or equality constraints. So always just remember to include the index even if you're working with a single constraint. Okay, so once that is done, then I have to just go over to grad FCH. And this is now once again the second example that I have over here. So I'm just going to uncomment this first lines over here, or comment that out, uncomment these lines. And now you'll see that I have GF1, 2, 3, 4, and each of them are then df over dx1, df over dx2, df over dx3, and df over dx4. And you can go and validate as well that these are the equations or the formulas that I get when I use the analytical gradient. Then for GC, you'll see that I'm working only in row 1. So this is this first index that I have over here. And this makes sense since I only have a single inequality constraint, but I have multiple design variables. So 1, 2, 3, 4. So this is dc1 over dx1, dc1 over dx2, over dx3, over dx4. Okay. And then lastly, I also have a similar setup for GH. So once again, only a single row that I have over here, 4 design variables. So it's going to be dh over dx1, x2, x3, x4 that I'm setting up over here. All right, so once that is done, then I just have to go and look at what the other inputs are that I have to give this system. So they give me the boundary conditions as well, and then the starting points. So let me first go and generate the boundary conditions. So it has to be between 1 and 5. So if I head back to my command window, I'm just going to say low is equal to, and let me generate, so this is for all 4 variables. So I'm just going to type in 1:4, and then comma, and then I can say, so this has to be 1, 1, 1, 1. Okay, so if I now press enter, you'll see that the form that I have over here is 1, 2, 3, 4 in the first row, and then 4 ones in the second row. So this isn't correct. I first have to go and convert this so that 1, 2, 3, 4 is in the first column, and then the ones are all in the second column. So all I'm going to do over here is just say low is equal to low prime. Right, so now it's in the correct form. Then I can do the same with up. So in this case, I'm just going to say up is equal to, once again, across all 4 design variables. And this will then be 5 across the board. And then I can just include the transpose as well. Okay, so now that is also set up correctly. And then finally, I just want to specify x naught as well. So that was given as 1, 5, 5, 1. Okay, so notice that I don't include a comma over here between the entries. This is the standard form that you give it in. You just place a space between the different variable starting arguments. Okay, so once that is then set up, I can just go and check whether there's anything else. So I don't have any convergence tolerances that I have to change. So in that case, I can just run then q. So I'm just going to say x if is equal to then q, x naught, which is my first argument, low, which is the second argument, up, which is the third argument. And then I can hit enter. Okay, so in this case, it now terminated after 6 iterations, but we can see that it took exceptionally longer than it did when we considered the fairly standard or simplified analytical equations. So when we had a single variable, it ran quite quickly. For 2 variables, it took more iterations, and now for this case where we have 4 variables together with inequality and equality constraints, we can see that although it took 6 iterations, the computational time was markedly longer. But nonetheless, if we look at the convergence behavior over here, we can see that the function value first started off with 16, but it ends at iteration 6 with a value of 17.01. And this is strange when we consider that the objective function should be minimized. So it doesn't really make sense that it goes smaller. We're going to investigate why this is the case in just a moment. If we look at the norms or the convergence behavior on X, we can see that it did terminate on the step size. We can see good convergence over there as well. -1, -2, -3, -5, and then -8 at the end. And then for the RFD values, it goes from -4 to -8 in these last 2 iterations over here. So this is also shows that we have some convergence over here as well. And then we also have x1, x2, x3, x4, which are given. I just typed it out over here as well using x. And then f is 17.014 at the end. Now what we perhaps more want to concentrate on is what happens to the constraints for this problem. So the final inequality constraint function value is given as this 4.41 times 10 to the power of -8. So you'll remember that if we have a tolerance of 10 to the power of -8 on the function values, then 10 to the power of -6 is our C limit. In this case, it's smaller than 10 to the power of -6, so this also shows good convergence over here on C1. On H1, this is now -1.7 times 10 to the power of -8, so also very close to 0. And we can also deem this appropriate. If we look at the final side constraint values, we can see that all of them are negative, so that is indeed what we want. The CX1 is just 10 to the power of -9, so very close to 0. But this makes sense when we consider x1. We can see that it is indeed, it is 1 at the end. So it's on that border that we specify for the boundary condition. So now if we look at the objective function history first, we can see that there is indeed an increase in the objective function value. If we look at the variable histories, we can see that they do plateau out after about 3 iterations or so. Now to investigate why the objective function increases, we can go and look firstly at the inequality constraint. And what you'll notice is when we go to iteration, let's say yeah, so iteration 1, we can see that the inequality constraint is actually greater than 0. So that's why it can't terminate over here on this 16 value over here. It needs to increase the value to 17 because this is the region where it actually finds that the inequality constraint is met. Yeah. Yes. Bye. 10 o'clock. Yes. Yeah.
I've just got some simulations.
Okay. Yeah. Yes. Not a problem. Cool. Awesome. All right. So then, if we also look at the lower limit inequality constraints, we can see that all of them are smaller than 0. So that also shows good convergence behavior over there. And then I also just want to look at the equality constraint values. And in this case, we can also see for these initial iterations where the function value was smaller, we actually have large values for the equality constraint function value. So this is a violation in the constraint, and it can't terminate based on the, well, it can't terminate closer to smaller objective function values. It first needs to specify or ensure that the equality constraints and the inequality constraints are met before it converges. Okay, so if we then just check over here, I think as well, so the objective function histories have been included, variable history, so you can just go through all of this as well if you want to check the convergence behavior. Now in our case, I just want to check, I think there is a point that we wanted to make just from this. All right, so it's not shown over here, but basically what this problem shows us is that with the increase in the computational effort, we can easily see that from the time it takes to solve the problem. So the more inequality, equality constraints, boundary conditions, all those things that we have, the longer the system is going to take to converge, even though it requires a fairly small amount of iterations. So it's always important to just consider the complexity of your problem as well, especially if we're going to look at the dynamics to see, are there any possible reductions that I can make to make sure that the system runs a bit faster. If I can maybe reduce the number of inequality constraints, that would also help the system out. Right, so I think just the last thing that I also want to show for this problem is then if we, instead of relying on the analytical gradients, we then make use of this finite difference intervals. I'm just going to comment this out and then we can uncomment this. Okay, so in this case, I'm now going to use the finite difference method, more specifically the forward difference method, to solve the gradients. As you'll see, if you try and do these gradients by hand, they tend to get a bit more complex if you have analytical equations where you have a multidimensional or something like a 4-variable problem. Depending on how that analytical equation is set up, it will take more effort to actually calculate these analytical gradients. So instead, if you're confident in this delta x value, so in this case it's 10 to the power of minus 8, which is a fairly localized gradient. If you're confident in this value over here, you can just rely on the actual forward difference method to solve the problem. Right, so in my case, I'm just going to use this. Nothing else really changed, so I'm just going to retype all of these things. And up, we also know, and x naught was also given. Okay, so now I can rerun the problem for the example, and then I'm just going to now make use of the forward difference method. Okay, so if I solve this problem, I can see that once again it terminated after 6 iterations, once again with a value of 17.01. There might be some more differences over here in the precisional values, but for our case 17.01 matches what we had for the analytical gradient values. If we now look at the x norm and RFD, we can see that at the end it's 10 to the power of minus 8 on the x norm and 10 to the power of minus 9 on RFD. So this actually shows better convergence behavior since we were able to terminate on both the function value and on the step size. If we look at the values for the inequality constraints. In this case, C1 is now 10 to the power of minus 7 or negative 10 to the power of minus 7. So this value is actually more negative than what we had for the analytical gradients. H1 in this case is essentially 0, so that's fine. And then all of my side constraints are also negative, so that's also correct. Okay, so if I'm not too confident in my analytical abilities to solve the gradients, I can just rely on the actual forward difference method to solve the problems. Okay, so another point that I just want to make is if we go back to example 1, and we perhaps reconsider this one, I might also be tempted to find the maximum value of the objective function. So in this case, it's this value over here. So I just want to find a local maximum in this case. And this is situated here between 0 and 1. Now the problem with the optimization is that you can only perform minimization problems. So once I want to go and try a maximization problem, what I first have to go and do is take my objective function and any gradient vectors that I have and multiply them with negative 1. In that case, I then essentially flip over this graph that I have over here, and then it's going to see this point over here as a minimum, and it can converge to that point. So let's assume that I want to use 0 as a starting point, and I want to find the maximum over here. So then all I'm going to do is head back to, let's do fch.m. So if I go back to example problem 1, I've already typed this one in. So all I want to do in this case is then place everything in a bracket and then multiply by negative 1. And then for grad fch, I'm just going to suppress this one since the analytical gradient is fairly easy to find. Okay, and since my objective function changed to a negative, I now just have to update my gradient vector as well and multiply that by negative 1. Okay, so everything else should be fine. So now I'm just going to say x naught is equal to, let's do 0.0. And then I can type in xf equal to din q x naught. Right, so now it converged after 5 iterations fairly quickly as well. It terminated on both the function value and the step size, which is good. And then if I check x1, I can see that it's 0.763. Now if I just go back to my analytical curve over here, I can see 0.763 sits somewhere around here. So it does make sense where it converged over here. It does seem to be at that local maximum that I have. If I then look at the function value, in this case, it returns minus 9.5836. But I now need to remember that I multiplied it by negative 1. So I need to go and flip the analytical or the graph back to its original state. So I'm just going to say f times negative 1, and then I get this 9.5836. If I go over here, I can see that this maximum does seem to sit somewhere between 0 and 20, more or less at 10. So that 9.58 value that I get over there does make sense indeed. Okay, so for any maximization problems, we just have to remember to flip our objective function over, and then we can essentially solve the problem as a minimization problem. Yes, yeah, it will. Yeah, so yes, yeah. So regardless of your dimensionality of the problem, when you want to perform a maximization, always to basically solve the maximum, you just first change it to a minimum. So you're always going to multiply by negative 1, even if you have 3 or 4 design variables, something like that. Yeah.
What instances can we not have like a proper conversion to?
So yeah, that's I guess it would be when you don't really have a specific minimum that you're going to be able to attain. So you might have like constant curve or something when you consider a specific variable. In that case, the system is going to struggle to find that minimum. if it steps to the left, then it's going to have the same gradient value as when it steps to the right. So it's going to struggle to converge. In that case, it usually converges very locally. So you'll see like a convergence after one or two iterations. Another case would be when you have discontinuities in your data, or you have like not really oscillatory, but noisy data or spikes in your data. So that is possible for the DAP-BC problems. Not really the problems that we're going to look at in the module itself, but you might have discontinuities, especially if you consider the trajectory that you're following with something. It might influence where you have discontinuities. Fairly close to the discontinuity, the gradient-based optimizers are going to struggle to find a minimum. Yeah.
Because I see in the first example, for instance, we look at a specific range.
Yes.
And I guess my concern would be like, what if we actually don't yet know that there may be like a local or global minimum?
Yes.
It might just be like a function that is just going up.
Yes. So in that case, what the system would probably do is, so if you have like where you start from a fairly small value and it goes up, then it will see that increase or the positive gradient. It will basically step it back to the left. So if you only running it for 0 to 10 seconds or something and you have that curve, then it would rather, it would rather terminate at the lowest possible value. So if you have something like a, if I perhaps draw it over here, so if you have a linear graph as well, and you have something that sits like this. So if I start, let's say at some sort of a point over here, if it now tries to step to the right, then it's going to have an increase in the function value or positive gradient. So the dynamic Q optimizer will then force it to the left over here. And it will continue to do that until, well, in this case, I would have to give it a bound. Otherwise, this linear line is just going to continue on. And if I give it that lower bound, then it's going to terminate over here on this bound itself. Yeah. Right. Okay, so any other questions before we move on to concluding remarks? Just check over here as well. All right, so it doesn't seem like we have any chat messages. Okay, so then I just want to go over the concluding remarks and what we basically found from these optimization-only examples. So firstly, dynamic Q is a fairly powerful gradient-based optimization method, which makes it ideal for function analyses where smooth curvatures are present. The computational efficiency, however, depends strongly on the choice of initial conditions, the number of design variables, and complexity of the function evaluations. And the initial conditions or the starting point will also influence whether the system converges to a local or a global minimum. So we always need to take into account where we start our design from. The dynamic Q, being gradient-based, is also susceptible to local rather than global minimization. We don't really have a dedicated tester to look at whether we found a global minimum. Instead, what we rely on is to perform multiple initial starting point conditions and then see which optimization is going to give us the smallest possible objective function. And that will then be known as the global minimum. Okay, so then lastly, the extension of the dynamic Q to the DAP-BC environment. And this is something that we're going to delve into in the next lecture, but just to give you a brief overview of what we plan on doing. So in this lecture, we have considered easily verifiable analytical functions for optimizations. Real problems, however, will most likely not have analytical representations, and we're going to have to rely on the results that we obtain from our data model, or from, in this case, if we're working with DAP-BC, what the output of the DAP-BC environment is going to be. And then since they also don't have analytical representations, we will also need to rely on finite difference methods to solve any gradient-based calculations. And we've now looked at a small example of that, but for the DAP-BC, we're going to rely strictly on the forward difference method to solve these problems. Now, DAP-BC is one such example where we don't have analytical representations. So the dynamic properties are calculated using iterative integration techniques. We know that we apply the Runge-Kutta methods over there. We have some Newton-Raphson schemes as well that we perform. So this already tells us that we're not going to be able to rely on some analytical function over there. Then we also have complex function evaluations that are performed, and depending on the different models that we use, those function evaluations can be quite large, or the number of function evaluations can be quite large. There may be noisy data present as well. In that case, we need to perform some sort of a filtering process. Now, for the problems that we're going to look at, the data that we have available is not going to be noisy. You're not going to have an analytical representation, but you do expect a smooth curvature when you're performing the calculations. Gradients can only be determined through the finite difference method, so that we said. And some optimization examples then, and how we extend the dynamic queue to the DAP-BC workbench is then given over here. So an example would be varying the length of a rotational acceleration, varying the length and rotational acceleration of a driven pendulum to minimize the moment at the pin joint. So this is something like where we looked at the pendulum rod initially. We can also minimize the acceleration of a tire during contact with the ground by varying the stiffness, free length, and damping associated with the suspension. So that would be something like the McPherson or the double A-arm suspension systems that we looked at. Minimizing the torque on the body of a cart by optimizing the wheel size, the aerodynamic drag coefficient, and maximum motor torque. Maximizing the speed of a conveyor belt subject to friction model parameters. So you'll remember from our application examples, we considered different friction models for that box that is basically connected to a spring system which moved on a conveyor belt. So over there we can also derive or define some parameters that we want to investigate. And finally, we can also look at determining the contact model parameters required to subject a falling rod to a specified acceleration. Okay, so you can also think of some other examples for this. I think the best would probably be if you consider your assignment 1, looking at what parameters you can perhaps vary over there. So as I mentioned previously, assignment 2 will follow on assignment 1. And if you have a good idea of how your system works, what the important parameters over there are, then you can sort of do some variation of those parameters to see how that's going to influence the system. Okay, but those are the type of optimization examples that we're going to look at, and we're going to start with that in the next lecture. For this lecture, we only focus now on the dynamic queue optimization. Okay, so any last questions before we conclude for today? All right, let me just check over here as well. All right, so I see we don't have any questions. Okay, in that case, we'll then pick up on this work again next week, Thursday. For now, I'd say maybe just try and use the dynamic queue optimizer for some analytical problems. You can go and check on YouTube as well. There are usually these type of physical applications of optimization. So perhaps you want to go and try that just to get a bit more familiar with dynamic queue. But then in the next lecture, we're going to investigate its integration with DAP-BC. Okay. But for this lecture, we can now conclude. So thank you.